Hey everyone, part two of the reasoning with sortedness bit. This time I want to talk about functions that preserve sortedness. So these are functions that take a list nat to another list nat, right? Lists of naturals to lists of naturals. And it says that look, if they started out sorted for some list AL, then f of AL is also sorted. So these are functions that don't change whether or not your list was in order. So we can look at a bunch of functions that preserve this. So for example, if we map successor over every element of a list. If it was started out sorted, it's still sorted. Everything's just kind of shifted by one. But if it was sorted, everything's in the correct less than or equal to relationship. Shifting everything by one won't change anything. A rising tide lifts all boats. I'll walk through this proof, but not the next one. How does this work? We say, okay, well, give me some list. Suppose that it's sorted, and now I have to show that my function preserves that sortedness, that if I run this function on it, it'll still be sorted. So here I'm going to do induction on sortedness, and we again get the nil, one, sorted cons cases. When you can, it is almost always easier, almost but not almost always easier to do induction on sortedness rather than on the list itself. Okay, in this case, straightforward. Here again, straightforward. Here, now it's interesting. The sorted cons case is really the only interesting case for sortedness. Okay, so let's see what we've got. We need to show that mapping S over x cons y cons L is sorted, assuming that x is less than or equal to y, and sorted YL, and then we know that the result of the rest will be sorted. Okay, let's see what happens. I'm going to simplify everywhere just to sort of get those successors in. And I'll say, well, look, if I know x is less than or equal to y, sorted cons has got me sorted, so to speak. So now I'm going to use again another one of these. Like I call this and its reverse NLEM and SNE. NLEM, SNLEM, and the reverse of that. These are like my mumble lemmas, like and it's like I can never remember which one I want. So just like it's one or the other, and then like apply it, and you'll figure it out. Eventually, you'll get better at it. Um, but so here, that lemma which says, hey, s of x less than or equal to s of y, well, it's sufficient to simply know that x is less than or equal to y, which we do know, and so that settles us. And at that point, we're just left with our IH. Right? Simple enough process to prove that add 1 is sorted. It's the same for add 2, you just have to do it twice, right? Not that big of a deal. But in fact, we can characterize a whole family of functions which preserve sortedness. Monotonic functions, right? A function is monotonic. If you give me an x and a y, where x is less than or equal to y, then my function's output will preserve that relationship, right? If x was less than or equal to y, then f of x will be less than or equal to f of y. So adding a constant, for example, is monotonic and will preserve sortedness for any constant. Every monotonic function preserves sortedness. Here, the proof follows exactly the same pattern as above, but rather than using one of these mumble lemmas, when we get there to sort cons, we need to show f of x is less than or equal to f of y. So before f was s or s of s or something. But now we just know monotonic f, right? Maybe make this clear. Unfold monotonic in HF. This says exactly what we need to connect HXY with our goal. So you apply it, you apply HXY, then the rest is the same. Okay, so we'd like you to combine these things you've just learned to prove a lemma that says, hey, adding any constant preserves sortedness. There are easy and there are hard ways to do this. Using lemmas can make this very easy for you, but you can also prove it directly like you've seen before. There are other operations that preserve sortedness. Filtering preserves sortedness. All you do is kind of like punching holes. So you're not adding anything, so it shouldn't be changing whether or not things are sorted. To prove this lemma, you're going to need this lemma. Proving this lemma is pretty tricky. You need a pretty creative helper lemma to prove this sorted filter cons. So this sorted filter cons is optional, but this filter preserve sortedness is not. Now, of course, you could use a lemma you haven't proved. There's nothing wrong with that. You won't be penalized or whatever. That's totally fine. That one's optional. Um, but this one is, I think, a little more interesting. There are easier and harder ways to prove this. So in any case, you'll need sorted filter cons. But if you're having a really rough time, maybe see if there's a different way you can go. The last thing I'd like you to do is to come up with a bad function. Um, what is a bad function? So here a bad function is a function that doesn't preserve sortedness, right? You should be able to prove that this bad function, when you map it over a list, if the list was sorted, the output will not necessarily be sorted. Okay. Once we're done with all these, once you've got these, I think you'll have enough practice under your belt to tackle proving our sort correct. Talk about that in the next video.